So today we're going to be covering a module on cardiac output. So basically the module will be explaining what your stroke volume is, what your heart rate is, what is the relation between the two components in determining the cardiac output, and the different methods that we're going to basically use to measure cardiac output. So cardiac output is defined as the volume rate at which the heart pumps the blood. Cardiac output is measured in liters per minute. In adults, cardiac output reaches a value between approximately 3 and 5 liters per minute. Quantitative definition of cardiac output is the product of stroke volume and heart rate, as it can be seen on the formula. The volume, the stroke volume will be represented by V and the heart rate by R. So let us look at cardiac output methods of measurement. So let's look at the blood flow measurement. So blood flow measurement can yield cardiac output data. Such instruments measure the blood flow rate, and the cardiac output is determined by integrating the flow of blood flow signal over a known period of time. Problem with this approach, transducer have to be directly applied to the vessels being measured, so which means the measurement has to be invasive. This requirement limits cardiac output measurement via blood flow measurement. So this is the method being described, which uses the electromagnetic measurement or electromagnetic sensing of the vessel itself. So this method basically measures or determines the amount of electromagnetic that is generated by the current, by the blood flowing through the vessel. So this will be induced on a coil, which will be measured by a circuit. So basically the output voltage of the signal from the flow of blood will be basically represented by this equation, where E is the potential in microvolt and Q is the volumetric flow rate in cubic centimeters per minute or per second, and B is the magnetic flux density in Gauss, and A is the vessel. So A is the vessel radius in centimeters. So this is the another blood flow measurement, which is basically based on ultrasonic measurement. So the Doppler effect is the key component, or the key sort of like basically what happens is one transmit in ultrasound using a transducer A, and the blood flow will cause a Doppler effect on the transmitted signal, and will either add or subtract frequency on that signal, and it gets reflected back to B, and the Doppler shift, the signal gets amplified first, and the Doppler shift will be detected from this detector here, and from then onwards, then we can filter the signal, amplify, using an audio frequency amplifier, You can listen to the sound on the earphones, or you can take the sound to a mixer, a trigger shot and one shot circuit, and integrate the signal and display it on the meter. So this is basically the voltage that is generated across flow velocity of the medium. So this is the average flow velocity of the medium, not the voltage. So it's represented by this equation where C is the speed of sound in the medium, and T is the difference between upstream and downstream times, and theta is the angle between the crystal axis and the flow axis. So let us look at the dilution technique. So most cardiac output measurements use a dilution technique in which a known concentration of some tracer material is injected into the bloodstream just before the heart. So the diluted concentration is measured downstream past the heart, thus yielding the cardiac output. This is commonly used, this commonly used tracer material is called endocyanine green. So the diluted concentration is measured distal to the heart, and the flow is given by the flowing formula, as we have seen before. So the dilution technique, so the cardiac output will be given by the injection rate of the endocyanine over the concentration, and this will yield the cardiac output measurement. So we have different dilution techniques. So the first one being your FIG method. The FIG method basically uses room temperature, or your room oxygen inhaled by the patient during normal respiration as the indicator. So the oxygen is injected into the system during the respiration. The infusion rate is determined by the measurement of the respiratory gases. So it is necessary to subtract the oxygen concentration of the patient's exhaled air from the room air concentration, normally taken to be 21%. So concentration is determined by measuring the oxygen concentration of arterial blood as it leaves the lungs. So the term arterial blood contains the error term because returning venous blood contains some oxygen. This amount must be subtracted from the arterial oxygen concentration. So repeated measurement made over several minutes are averaged for the final results. So we have another dilution technique called the dye dilution. So dye dilution uses either an optical dye such as endocyanine green or radioactive tracer dye. In the optical dye case, the dilution curve is measured by a light densitometer, and in the latter case, by a scintillation counter or gamma camera. So figure below shows the concentration at the point of measurement distal to the injection site. Shortly after injection, the concentration at the measurement site rises abruptly to a maximum value and falls exponentially as the injected bolus passes the point, as can be seen on the diagram. This exponential decay is caused by the injected bolus not remaining as a lump, but spreading out, diluting over a long path as blood flows. So this will be the injection. It goes up, reaches maximum concentration, and it will exponentially decay as the blood flows. So cardiac output is then measured by integrating the concentration curve. So the blood flow rate in this case will be equal to K times M, where K is the constant usually to 150, depending on injectate. And M is the volume of the injectate, and where C is the concentration. So another method that is commonly employed is thermodilution, which is one of the dilution techniques. So thermodilution has become one of the most common methods for measuring of cardiac output and form the basis of most modern cardiac output computers. The injectate used is ordinary for solutions such as saline or 5% dextrose in water. And most thermodilution computers or cardiac output computers operate on a version of the following equation. So basically, this is what would be programmed in the computer so that the dilution or thermodilution method can be effective. So GB in this equation, or K in this equation, is a constant of approximately 20 to 150, and GB is the density of human blood in kilogram per cubic meters. And GI is the density of the injectate, and VI is the injectate volume in liters. So UB will be the heat energy content in the blood in joules. UI is the heat energy content of the injectate in joules. So TI is the pre-injection temperature of the injectate in degrees Celsius. And TB is the pre-injection temperature of the blood and in degrees Celsius. And T stroke B is the post-injection temperature of the blood at the measurement site. So this is basically a thermodilution computer which uses a bridge, Wheatstone bridge, as a sensing element, and it has a preamplifier, and there's an isolator which goes to the recorder output. There's an integrator of the signal coming from the amplifier, an analog divider to divide KV over VY, which is also going to include these factors: the pre-injection temperature of blood and injectate, and it will come to a filter to a digital panel to be displayed as the cardiac output. So this is a thermodilution computer. This is a simplified circuit diagram of it. So those are your references. Should you require more information, you can visit the references. Thank you.